Hello everyone, my name is Wai Tong, currently a fourth-year PhD candidate at the Hong Kong University of Science and Technology. In this video, I will present our paper, Exploring Interactions with Printed Data Visualizations in Augmented Reality. Direct manipulation is important in data visualization. It helps users to explore data and engage in data exploration. Generally, the interaction with data visualization involves two layers, physical layer and logical layer. Physical layer represents the interaction between the user and the instrument. Logical layer represents the interaction between the instrument and the visualization. How to achieve direct manipulation on both layers? For example, at the logic layer, we can use the mouse wheel to achieve zoom instead of clicking the zoom in and zoom out buttons. However, at the physical layer, the interaction used mouse and keyboard limits the direct manipulation. For example, touchscreens provide more direct interaction, such as touch and pinch, than the mouse and keyboard. Second, current direct manipulation with mouse and keyboard are limited by the visibility and understandability of interaction affordance. People might not be aware of the interactivity of the data visualization. To further push forward the direct manipulation, researchers investigate different modalities. For example, with the use of natural language processing, people can communicate with data visualization directly. Data visualization allows people to view the data with their hands and body. Recently, augmented reality has brought us a new way to interact with virtual data in reality, as well as the ability to combine with physical objects for visualizations and interaction. In particular, tangible objects like paper sheets, customized embodied axes, and globes can be used to interact with 3D scatter plot, three-dimensional data, and spatial data in AR. Following this line of work, we explored paper sheets as tangible means to interact with data visualization printed onto these paper sheets under AR, because paper sheets is the most common physical medium for distributing data visualization. Moreover, paper provides a rich set of interaction affordance we can use as a touch surface, which can also be moved and rotated in space. We can furthermore fold it, bend it, or even tear the paper apart. Besides, with the help of augmented reality, we can better embed the physical parts with the logical part, leading to a greater sense of directness. For example, we can stack two papers to merge two bar charts into a grouped bar charts directly. However, interactions with printed data visualization is still underexplored. Therefore, in this work, we are interested in exploring how far can paper support direct manipulation for data visualization. Specifically, by using instrument interaction framework, we formulate our research questions as what are the actions and commands that can be supported by paper? To answer this question, we first perform literature survey to understand the existing paper interaction taxonomy as actions and low-level data visualization tasks as commands. Then we conducted an ideation workshop to collect possible interactions that maps the actions to commands. We invited 20 participants, mostly HCI and VIS PhD students, to read 5 printed data visualizations and think about what they want to explore more from the printed visualization and how to do it. To accelerate the brainstorming, we provide actions and commands prompts from existing taxonomy. After receiving 146 ideas, 2 authors first extracted the visualization tasks and actions from each idea. Then we grouped similar actions and commands to form 81 unique interactions, such as selecting single marks by pointing. We found 10 visualization tasks and 19 paper actions in total. Based on the interaction, we constructed a design space with 3 dimensions: commands, degree of information, and the number of paper sheets involved. The first dimension describes how the visualization reacts to the paper action. For example, the underlying data could be filtered or sorted, and the data visualization can be zoomed and panned. The second dimension describes the type of information involved in the interaction, such as Boolean information and positional information. With more degree of information, users can have more control to the visualization. The last dimension is the number of paper sheets involved. This dimension describes the number of papers used in an interaction. By specifying the number of papers, we can determine whether the interaction targets on a single view or multiple views. Moreover, it can tell whether the interaction involves one hand or both hands. We can then describe the interactions collected from the workshop using our design space. For example, shake to reset is a Boolean interaction for record, and collates or collocates to select and link is a multi-paper position interaction for link and select. Moreover, our design space provides an overview over the visibility of the interactions. For example, we cannot shake to select a mark because shake action only provides a Boolean input to the selection command. It will make the system confused which particular data points need to be selected. Designers can look up position and area interactions to choose an appropriate action for the selection command. After constructing the design space, we further investigated the core idea of our work, interacting with printed visualization. We conducted a user study with 12 participants to understand users' preference and the viability of proposed interactions. We implemented a subset of 11 interactions and let the participants to try them one by one. After that, participants need to pick one action for each command to complete the data exploration task. The results showed that most of the proposed interactions were intuitive and engaging to use. Moreover, all participants were able to use the chosen interactions to perform data exploration. Based on the results, we derived 6 design implications. The first one is to provide redundant actions to point action. Point actions receive most of the positive rating in all aspects due to familiarity. However, it's error-prone. The pointing gestures are not recognized when there is occlusion. Since paper provides rich affordance, we can afford other actions with similar rating, yet easy to recognize, such as tilt to pen. The second implication is to make use of different actions for command shortcuts. For example, when the data is biased, fold to zoom might be better than pinch to zoom. The third point is to support both selection and inverse selection for cover. That's because when the paper is getting larger, it's harder to cover all the unwanted area for selection. The fourth implication is to utilize the semantic meanings of paper actions when designing interaction. For example, tilt to pen got higher scores in both intuitive and engagement because it's similar to water falling off. The fifth item is to balance the intuitiveness of actions and readability of text. For example, translate to zoom is intuitive because it matches the physics that close objects become larger and far objects get smaller. However, the text is getting harder to read when it's too far away. One solution is to fix text at a certain distance for reading and allow the visual pattern to follow the action movements for intuitiveness and engagement. Last but not least, the physical properties of paper could also affect the choice of action and command pairs. For example, if the paper size is too big, it is hard to fold the paper for zooming. If the paper is heavy, it is not a good idea to involve too many spatial actions. To conclude, we have presented a design space to describe paper interactions for data visualization in AR. We also conducted a user study to show that the proposed interactions are intuitive and engaging to use. Also, the users can use the given paper interactions for data explorations. Lastly, we derived 6 design implications for future designs. That's the end of this video. Thank you for your watching. If you are interested in more details, please read our paper.